Hi, everyone. Let's talk about acids and bases. Acids and bases. Wow, it's a whole subfield of chemistry, and it involves H plus ions. And we may have mentioned this before in a previous video, but what is a hydrogen ion? Hydrogen cation. Hydrogen is the first element on the periodic table. It has one proton and one electron. And if it loses that one and only electron, you just have a naked proton. That's not even an atom. That's very reactive. And that is an acid, or actually the most important feature of an acid. So let's talk about reactions involving H+. The acid-base reactions, let's increase the pen size here. We can also call those neutralization reactions. And that's because H+ will be reacting with something else to get rid of the positive charge and its reactivity. You'll get access to more electrons and actually turn into an atom. Okay, so you can call these acid-base reactions, or you can just call it the neutralization reaction. And as I try and follow all this information about chemistry in my head, one way of doing it, that I do it, maybe you can do it too, is to remember definitions. And then you can use those definitions to kind of figure out the problems that you encounter on exams or in real life, wherever you encounter chemistry. So these are two important definitions that I think are helpful. First one is acids donate H+. Acids are molecules that fall apart and out pops an H+ ion. And this important subfield chemistry, other chemists are going to help us out. So usually, if we see a chemical formula, the H in the chemical formula will be listed first. So here's some very common acids. We have hydrochloric acid, found in stomach fluid, and the H is listed first. Hydrobromic acid, yep, H first. Sulfuric acid, there's two H's. Yeah, sulfuric acid can release two H+ ions. And then this molecule is acetic acid. It's found in vinegar. And if you look at the chemical formula, I should finish writing. Vinegar. If you look at the chemical formula, there's actually 4 H's in the molecule, but vinegar, or the acetic acid molecule, only releases one of those 4. So we list 1 hydrogen in the beginning, and the other 3 stay behind. Okay. Otherwise, if someone wanted to be a little misleading, you might list all 4 H's together as HC2H3O2 and be like, yeah, guess what that molecule is? That's not so helpful. Put the H first so we all know, hey, let's suspect it might be an acid. Acids donate H+, so then do the opposite for bases. Bases will accept those or take them on. And there's 3 general bases that we encounter in general chemistry. There are others, but these are the 3 main ones. Many of the bases have a hydroxide ion in their chemical formula. So here's sodium hydroxide, potassium hydroxide, or even calcium hydroxide. If we look at our solubility rules though, sodium, potassium, they're alkali metals. Yeah, if you find those in a salt, in an ionic compound, it's very likely to be water soluble. But if you go through the solubility rules with calcium hydroxide, you discover that's not very soluble. No. So this is not a very strong acid, strong base. It's not very strong because it doesn't dissolve, not very well. And if you mix it with an acid, the acid can start to react on the surface of the solid calcium hydroxide, so it can react, it will react. But it's a little slower than the others, a lot slower actually. Okay, so look for OH in the chemical formula to identify any bases. But ammonia, all by itself, NH3, is also a base, as is the carbonate ion. That's one of our polyatomic ions, CO3 with the 2-. And you might find carbonate in sodium carbonate, potassium carbonate, or even calcium carbonate. Yeah, I just decided to pick the same cations as before. So that's the idea. You can put other cations in front of hydroxide and carbonate and create other bases. Quick little note about calcium carbonate. If you look at solubility rules, it's also not soluble. Yeah, calcium carbonate's found in limestone and in seashells, but they'll dissolve in acid because they are bases. Calcium carbonate is. Okay, so what's going on here? After we identify acids that donate H+, bases that accept the H+, they come together and neutralize each other. And then what are the products? Well, generally the products are going to be a salt. And in our examples, I'll try to remember to point that out. So salt, a cation with an anion, an ionic compound. And then something else that contains the base. So we had 3 bases now, hydroxide ion. Well, run through the definition. What's a base? An H+ acceptor. Okay, hydroxide ion, you're a base, so here's one more H, and the H carries a plus charge. So now what do these 3 atoms turn into? Well, now the O has 2 H's. Oh yeah, that's water. And then hydroxide had a negative charge, and it neutralizes the positive charge. So there's 0 charge in water. There you go. Some students just memorize it. I use the definition. It's like, what's hydroxide make? Oh, wait, hydroxide is a base, H+ donor, acceptor. H+ acceptor. So give hydroxide another H. Oh yeah, it had 1 H, so then it has 2. And then cancel out the charge. Ammonia, oh yeah, you're a base. So ammonia is N with 3 H's. Well, give it a 4th one. Ooh, there it is. Oh, and ammonia has no charge. There's nothing written up in the top right here. 0 charge. Right. So over here, there is a -1 charge listed. This ammonia didn't have anything. It's neutral. So when it takes on an H with a positive charge, the whole thing still is positively charged. And we recognize that hopefully as one of the polyatomic ions, the ammonium ion, NH4 with a positive charge. Third base we discussed a minute ago is the carbonate ion. It's a little different than the other bases. First of all, it has a -2 charge, which if you want to neutralize each other, you're going to need 2 H+, right? -2 will need a 2+. So 2 hydrogen ions. And then together, okay, carbonate, you're a base, you're an H+ acceptor, so CO3 2-, here are 2 H's, there you go. Are you happy now? No. No. Why? Why not? Well, nature, she makes the rules. This molecule is carbonic acid, and for some reason, it's not happy, and it quickly falls apart. And it falls apart to produce water and carbon dioxide. Water is really stable, so is carbon dioxide. So that's probably the driving force. These are very stable molecules. Very common too, right? What's this picture? Oh, because it's an acid-base reaction. Here's Alka-Seltzer. Airborne tablets also do this too. There's other pharmaceuticals that do this as well. Inside the tablet, there's a mixture of compounds. And 2 of the compounds in here are acids and bases in the solid form. And as a solid, they're not able to move around and react with each other. So you put the solid tablet into water, the compounds start to dissolve, and then the acid and the base find each other. And guess what? The base in here has carbonate ions. So whatever acids in here will donate H+, acids donate. Carbonate will accept it. That's what bases do. You get carbonic acid that will fall apart to produce more water and all these little bubbles that you know as carbon dioxide. Cool. Okay, let's end this video with 2 examples, something you might see on an upcoming exam. Move this down here. Okay, so sample problem, again, homework problem, exam problem, final exam question. Write a balanced equation, and here I want the full chemical equation. Ooh, and I also want the net ionic equation, so need 2 equations. For what? For the reaction between, okay, so we can go to the periodic table and find CS, it's cesium. And then OH, well, that's one of the polyatomic ions we should memorize. It's hydroxide. This molecule is cesium hydroxide. And, ooh, we found OH. It's probably the base. This molecule has some H's listed first. Yeah, that's the acid. And the fact they found OH and H tells us this is probably an acid-base reaction, not an oxidation reduction reaction, and probably not a precipitation reaction. Cool. What else? If you're curious, I'm not sure if you had to memorize this polyatomic ion. That's oxalate, C2O4 with the 2 minus. Anyways, if you're curious, this is oxalic acid. You don't need the names, just thrown out there. Interesting information, I hope. All right, let's do this. Write the balanced chemical equation. Okay, so that's going to need some reagents, and we're told what they are. CSOH and, oh, let's write it down, CSOH and H2C2O4. Now, we already identified that this compound on the right is the acid. And if you like, you can list it first. The order of your reagents and products is not important. It's not required. There's not a standard way of writing it. But most people put the acid first. So you can rewrite it that way if you like. Whatever. How do we get the balanced equation? Well, there's 3 things we have to do. First, we got to find the products. Then we have to balance the equation. And then we have to put in the physical states. And I like to try and do it in that order and not try and do more than that at a time. I'll explain what I mean in a second. First step, let's find the products. So we got a couple of clues already. This molecule has an H listed first. It's going to produce H+. There's an OH here. It's going to produce OH-. And hey, we just saw a few minutes ago, OH-, what's your task in life? It's a base. It accepts H+. Okay, so we should probably give this an H+ and turn it into water. Oh, wait, so what's happening then? The H from one molecule is going over to the OH. And then after you make water out of the hydroxide ion, is cesium going to stick to water and make a molecule? No. Cesium is going to follow the negative charge. H comes over to the left, cesium goes to the right. If you need a word for it, it's double displacement. It's a double displacement reaction. I like to think of switching the cations. So what's the cation in cesium hydroxide? It's cesium. What's the cation here? It's H+. And I know there's 2 of them, right? There's 2 H's listed first. And yeah, there should be a 2 here. But wait, that's part of balancing the equation. And right now, I just want to predict the products. So ignore the 2 for now. We'll do it in the next step. Okay, so what is the cation? It's H+. What's the anion? It's the leftover piece after the acid kicked out its H's. It's oxalate, if you want a word for it. And it must have a -2 charge. Now, I got it memorized, but if you don't, that's okay. Just remember that H is listed first, and H comes off as H+, a +1. And since there's 2 H pluses, and this whole molecule is neutral, that must mean that the leftover piece has to be a -2. That because the whole molecule needs to be neutral to be a stable compound. Okay, so you didn't have to memorize the 2 minus, you can figure it out. 2 H pluses go away, leaving the resulting fragment as a -2. Let's switch to cations, figure out what the products are. So this one and this one trade places. So H+, you go hang out with hydroxide ion. And cesium, you're over here with oxalate. Whoops, don't make a molecule yet. You gotta check the charges. Cesium and oxalate. Okay, we have to check the charges. So we'll do the first one first because it's easier. The H+ comes over with 1 + 1. Hydroxide has a -1, and they immediately cancel out. The +1, the -1 cancels out. Yeah, and your product is water. Combine all these atoms together. Do the same thing here. Combine all these atoms together, and a +1, ooh, does not cancel out the -2. We need a second cesium so that together there's a total of +2 to cancel out the -2. So then in the correct chemical formula of the product, there's 2 cesiums and 1 oxalate. That's the right formula. Cool, we just finished balancing. So we did not. We finished predicting our product. Sorry, got ahead of myself. To make a balanced equation, 3 things are needed. Predict the products. Check, we did that. Next, we need to balance it. Third, we need to put in the physical states. Oh, I was going to remind us about the product of an acid-base reaction is usually a salt. Here it is, cesium oxalate, cation, anion, and then the product from the base. So hydroxide is the base, it grabbed H plus to make water. Nice, so that's the usual pattern for acid-base reactions. All right, step 1's done. Predict the products. We still got to keep going and balance it. So I'm going to grab the equation and go find a place with some clean space and start balancing it. Cool. All right, so to balance the equation, I like to save the simplest molecule for last. So as I look at this molecule has 3 elements, CS, O, and H. This one always has 3. Water, there's only 2 elements here, H and O, hydrogen and oxygen. Yeah, water is the simplest looking molecule. So my strategy is save the simplest molecule for last. Don't balance this molecule yet, and don't balance the H's and the O. Go after somebody else. Go after cesium or C, cesium or carbon. And then you just pick. Cesium, how you doing? Not too good. There's 2 on the right, only 1 on the left, so we need a 2 here. Carbon, you're next because I'm saving the H's and O's for last. There are 2 C's on the right. That's a CS, that doesn't count. Here are 2 carbons. Ooh, good, carbon, you're balanced. Thank you. That's it. We're left with the simplest molecule for last. How are the hydrogens doing? There's 2 on the right. Ooh, there's 4 on the left. There's 2 right here. 2 times 1 H is 2, and the 2 more. Okay, I got 4 H's on the left. Yeah, I need to fix that with the 2 here in front of the water. Now I have 4 H's on both sides of the equation. It's balanced. Good. How's oxygen doing? There's 2 oxygens in the first compound there. There's 4 more. That's a total of 6. 6 O's on the left side. Ooh, this is looking good. There's 2 O's here, and another 4 is also 6. Step 2 is done. It is balanced. Now we need the physical states. Okay, for that, use solubility rules and your knowledge, your experiences to help you out. So, cesium hydroxide, is that soluble or insoluble? Well, the first solubility rule says the ammonium ion and alkali metal ions are usually soluble. So go to the periodic table. Sorry, I didn't print one, but cesium is an alkali metal. So this should be soluble by the first solubility guideline. How about this one? H2C2O4. Well, okay, so now we're in trouble. Is this an ionic compound? Hydrogen is a nonmetal. Carbon is a nonmetal. Oxygen is a nonmetal. This molecule is completely covalent. And only the ionic compounds can use the solubility rules. So now we don't know. The problem should have told us. So on my exam, I left that information out. I should not have. I should have put a little AQ here because we don't have the information. It's not something we had memorized or solubility rules where we could figure it out. We don't have the information to know that this molecule is soluble. Okay, so that was my bad as an instructor. I didn't write a very good problem. On the exam, I will catch that when I answer, when I grade it, and I will realize, wait, you didn't have enough information to predict this, so I can't count. That won't count against you if you didn't say AQ. Water, what is physical state is that? It's also a covalent compound. It's not in the solubility rules, but that's okay, right? The most common form of water at room temperature is not ice or steam, it's liquid. Okay, so that one you should know from your experiences. And then this crazy molecule, well, it also has cesium in it, a metal, and C and O's are nonmetals. Nonmetals with metals make ionic compounds. We can use the solubility rules And again, cesium is an alkali metal, which makes these salts, these ionic compounds, soluble. Hey, we're done. We got the full balanced chemical equation. The full chemical equation. But now we need the net ionic. So what I do is I go after the full or complete ionic first. And all you do is you change your AQs to ions, if possible. Okay, so yeah, let's just do it. Okay, CSOH, well, yeah, that's ionic, it's aqueous. They separate in ions. Once it dissolves in water, the CS does not hang out with the OH minus, they separate. And then for every, the CSOH molecule has one CS, but there was two of them, two molecules. So we have two ions that have a +1 charge. And then the hydroxide ions swimming around the water in the aqueous solution as OH minus. This molecule, okay, so now we need some help. Why is H listed first? Oh yeah, because it's a acid. It's gonna come off of H2. No, it doesn't. Okay, so be a little careful. The H's do fall off, but they don't stay together, stuck together. That's a molecule covalently bound together. Two H's are nonmetals that would stick that way. No, they come off as H pluses. There's two H pluses. Same charge, repel each other. They're not going to stay stuck together. So the two up front means you have an H plus at one part of the liquid solution. There's another H plus somewhere else that came from this acid. Cool. Okay, and what's the leftover piece after two H's fall off? It's the C2O4 with what charge? Well, there's nothing listed in the top right. This is neutral. If something neutral kicks out two pluses, you have to balance a charge. The leftover piece must be 2 minus. And I forgot the physical states. Yikes, put them in. Cool. This one's not AQ. It's also water. Water is a covalent molecule. It's not going to fall apart as it's in water. Water in water. What? Just leave it as water. There's two water molecules. On the product side, cesium with nonmetals, metals with nonmetals. This is ionic. It's AQ, separating the ions. There's two cesiums, so we write CS2. No, we don't, right? The cesium, go to the periodic table, or go to the beginning of this equation. Cesiums have a +1 charge. Two +1 charged ions are not going to stick together. They repel each other and separate. And then the oxalate, 2 minus in physical states. Put them in. And we have the full ionic or the complete ionic equation. This is a teacher. If I'm the student doing this exam question, I just gave the teachers some bonus work here. He or she didn't ask for the full ionic, but there you go. I need it so I can get to the net ionic. Okay, so now we're at the full ionic. Let's go after the net ionic. And all you do is you cancel out the spectator ions. Cancel out spectator ions. Spectator ions. Sorry. Come on, spelling. There we go. Okay, so what we do is we see if there's some lazy ions in here. And yep, there are. Cesium, you were plus and aqueous. What are you doing afterwards? Still plus and still plus charge and aqueous. You didn't do anything. You're just watching someone else do all the work and change into a product. You're a spectator. Hydroxide ion, are you lazy? Okay, I see a OH minus AQ. Any OH minus AQs over here? No, there's no OH. Hydroxide ion is doing something. You stay. You're not spectating the action. H pluses? Any H pluses over here? No? Okay, cool. C2O4 2 minus. There you are. What? You didn't do anything. You're out of here. You're spectating the action. Cool. So then write what's left over. 2 OH minus. You got 2 H pluses, right? This thing, that thing, they survived. They didn't cancel out. And then over here is just 2 waters. Okay, if you leave this, I will take off like a half a point because it's fundamentally correct. But usually our balance equations are in their lowest forms. 2 OH minuses plus 2 H pluses make 2 waters. We just write OH minus plus H plus makes 1 water, right? So divide the whole thing by 2, and then now you get full credit. This is also the neutralization reaction. So if there's a homework problem that asks you to write the neutralization reaction, it's looking for this net ionic equation where H plus is from an acid, H plus donor, is reacting with the base, H plus acceptor. In this case, it's hydroxide ion. Let's see, let's do one more sample problem. We'll call it quits. This one's kind of fun. This is the Alka-Seltzer or the airborne tablets problem. It's also hopefully not a reaction happening at Costco. That would make a big mess. Yeah, you're definitely playing a dangerous game there. Okay, so we're going to write the balanced chemical equation and the net ionic equation between the molecule found in vinegar. Yeah, this container's on the left. It's HC2H3O2 and baking soda, which is this packaged compound over there. And the chemical formula is sodium bicarbonate. It is. Let's get a little more space here. Okay, so we want the full chemical equation. So you got to go get the products, then you balance it, then you put in the physical states. Let's get the products. Let's switch to cations. So what are the cations? This one's got H listed first. There's our acid, H plus donor, and that H plus is a cation. The leftover piece, hopefully you recognize that as one of the polyatomic ions. That's acetate. What's here? We got Na, an H, a C, and an O. Wait, H, C, O? Those are nonmetals. They're attached together covalently, but the sodium's a metal that's going to be ionically bonded. Na plus, the leftover piece then must be negative, right? The whole thing's neutral. There's one Na from the periodic table has a +1 charge. The other piece must be a -1 charge. Or you remember your polyatomic ions. This is bicarbonate or hydrogen carbonate. We got our cations and anions, so switch the cations. So H plus, go hang out over here. Na, go to the left. So Na, you went to the left. You're going to hang out with acetate. H plus swings over to the right. It hangs out with the bicarbonate ion. Okay, so some of you are saying, wait, I thought you said the 3 bases were hydroxide ion, ammonia, and carbonate, CO3 2-. Yeah, we'll have to throw this one in there too. I don't know if you needed that information knowing that bicarbonate, I don't think you needed to know that bicarbonate is a base. It is. The H is also listed first, however. What does that mean? Yeah, it's also an acid. That's kind of cool. This molecule can act as both as an acid and a base, and life depends on it. Right now in your bloodstream, there are a lot of this bicarbonate ions circling the bloodstream. And if you eat some lemon, something sour, something that has some natural acids in it, this molecule can act like a base like it does here. It can accept an H plus. These combine together, the plus and the minus cancel out to form H2CO3, and that's not our final product, right? We'll have to remember that's carbonic acid that falls apart to produce water and carbon dioxide. Wow, handwriting. Okay, so in the bloodstream, you know, it's your digestive process. Things go into the bloodstream, circulate the body, the nutrients and stuff. So the acids that get pulled out of the stomach or the small intestines, the carbon ions in the bloodstream will cancel out those extra A pluses and keep the pH stable. They'll buffer it. And then if you have to have eat something that's alkaline, something that's basic, then carbon ions in the bloodstream can also donate an H plus. Okay, so that's cool. Extra information. Sorry, I kind of got distracted there. Just by switching the cations, you put the H plus with bicarbonate and opposite charges attract. The C would then have 3 O's and 2 H's, and then hopefully you'll recognize that formula is not as the final product, but something has to fall apart and produce water and carbon dioxide, which are the final products. And then our salt, ooh, we're gonna get water, well, sorry. The base, which kind of is carbonate, produces water and carbon dioxide. And then you also get a salt, and here it's just Na with acetate. Charges balance, so nice. Just write all those atoms together, and you got the chemical formula of the salt, one of the products. Yay. Okay, I think we're good on predicting the products. Next, we got to balance it. So let's go to the right where there's some more room. To control paste. And we're good. All right, save the simplest molecule for last. Which of these appears to be the simplest? I would say the water again, or the carbon dioxide. They both work. So which one do you want to do? Water? I don't know. Save that for last. You could save carbon dioxide for last. Or maybe save them both. Don't balance the HO or the C's. Go after the Na. All right, how we doing? We got one Na on both sides. Sweet. All right. Let's do C next. Maybe I'll save water for last. Okay, C's. There's a total of 3 on the right side. Hey, there's 3 on the left side too. Awesome. All right, save the simplest for last. Let's go after H's and O's. H, I got 1 here, 3 more, there's 4. There's the 5th hydrogen. On the right side, I got 3 and 2 more. Hey, that's 5 also. Oh my goodness, is this already balanced? Got 2 O's and 3 more makes 5 oxygens. 2, 3, 4, 5. Yeah, everything's balanced. Love that when it happens. Cool. Step 2's done. It's already balanced. Now we need the physical states. Okay, so let's go back and look at the problem. We are told this molecule comes from vinegar. Okay, so this is the case where you would use your common experiences. Hopefully you've seen vinegar before or had Italian dressing on your salad that has vinegar in it. Vinegar is a liquid, right? It's a solution. So this molecule, it's actually an aqueous solution. Anyways, this is dissolved in water. Vinegar is mostly water, has that molecule and has some other things in it, gives us its flavor. So I'm hoping that from your knowledge of what vinegar is, if you saw on the grocery shelf, it's an aqueous solution. This molecule has Na in it, an alkali metal, and then we have a bunch of nonmetals, actually polyatomic ions. This is a salt, an ionic compound with sodium in it. And the solubility rule says sodium salts are usually soluble, AQ. Here it is again, sodium salt, AQ. Your knowledge about water, it's a liquid at room temperature. Carbon dioxide, what's your knowledge about that? It's a gas, a fizzing gas. It's one of the gases you exhale. So again, there's the common experiences, you'll be able to predict the physical state. Ooh, we're done with the full chemical equation. Nice. Okay, let's go after the full ionic. Change all AQs to ions. So here's an AQ. Is this going to form ionic? Well, the H is listed first, so yes. This molecule is an acid, so donate your H plus. That's 1 ion, a cation. The leftover piece must be negatively charged since 1 positive thing fell off of it. Or use your knowledge of polyatomic ions. You make acetate, that's soluble in water. By the solubility rules, actually, acetate salts are soluble. Sodium, yeah, you come off as Na plus, AQ. The remaining piece is another polyatomic. Gosh, it's really helpful to know your polyatomic ions. Got sodium again. Got acetate again. Oh, that's kind of redundant. What's going on here? That's okay. Got water. Okay. First thing, we don't have to break into pieces. Water, you stay together. And I really don't have any room, so I'll put carbon dioxide. Hey, these are a bunch of nonmetals. They stick together through covalent bonds. And it's not AQ. So leave that. We're only changing our aqueous things into ions if they separate, if they're ionic. Oh, time for the net ionic equation. We got the full ionic equation. So what do we do to get to the net? Cancel out the spectators. Get rid of the things that are lazy. H pluses, are you lazy? Make my arrow a little bigger so I know which side's the product and which side's the reactant side. No, there's no H pluses over here. Okay, you guys can stay. Acetate, what are you doing? Nothing. You're out of there. Sodium, ooh, you're lazy. Sodium usually is. The alkaline metals are usually spectator ions. Bicarbonate, you survived. You're doing something. Nice. Okay. We cancel all our, we look through all the reagents on the left and cancel them out if they can cancel on the right. We're done converting. Let's just list what's left over. We got an H plus that survived. We got bicarbonate. We got a water molecule that's liquid. And we got carbon dioxide, which is a gas. And there's our net ionic equation. It's also the neutralization reaction for the bicarbonate ion. That's supposed to be EQN. That's my abbreviation for equation. Nice. I hope that's helpful. Have a good day. I'll see you in the next video.